Okay, welcome to another Ginger Mathematician video where I'm going to go through some of the harder questions from the IB HL Applications Interpretations Paper 2 that was recently released by the IB to help students like yourself revise the IB. So let's get started. So Jorge is carefully observing a rise in sales of a new app he's created, and he's got a table of data. And he believes the increase is exponential. That's very nice if it's happening. And proposes to model the number of sales in month T with the equation as follows. And we need to show that Jorge's model satisfies this differential equation. So to solve this for 2 marks, we're going to take our function of n. So n is equal to a e to the power of rt. And we're simply going to differentiate this with the rules that we know. So to work out dn by dt, all we have to do is take the coefficient in front of the t, we bring that to the back, so we get r. This constant stays the same, and then remember with the exponential function we differentiate it. This is why it's amazing, it doesn't actually change, so we get e to the power of rt. Now you're probably thinking to yourself, well, how does this link in with the question as asked? Well, if we substitute in the initial equation, so sub n is equal to a e to the power of rt, into this equation, so we're replacing this part with n, then we do get the equation that we wanted, which is dn by dt is equal to r times n. So it does satisfy the differential equation that we see. Now, there's an interesting way they've approached this for the rest of the question here. They've done an Euler's method question, but they've actually done it for you in certain steps to also fit in some statistics as well. So we're given an adaptation of Euler's method. So we're using a step length of 1 month. So let's keep that in mind. We'll talk about that right at the end. The solution to the differential equation can be approximated using Euler's method, where n brackets n plus 1 is approximately equal to n plus 1 times, this 1 comes from the step, times the differential of n. And we somehow need to show from here that r is equal to this expression. So I'm going to take this expression, and being 1 times is going to make our life a little bit easier. So I'm going to write this over here. So n open brackets n plus 1 is equal to n with respect to n plus the differential of it. I'm just going to rearrange this. So I'm going to minus the n from both sides, not a differential, but this function here. So that gives me n dash of n respect to n equals n plus 1 minus n bracket n. Okay, like so. However, in this equation here, if I rewrite this in slightly different notation, essentially what this is saying here is that n dash, which is another way of saying the differential, is equal to Rn. So I'm going to substitute that in. A lot of substitution in the first part of the question here. Let me just get up a different colour pen. So I'm going to substitute this expression for my differential. So I'm going to replace this with Rn. So let's do that. So we get Rn respect to n is equal to n plus 1 minus n. And often with these paper 2 questions, they want you to lead on from something you've already done. So if you're stuck at this point, think, what have I already worked out? How can that be useful in this question? And at this point, all we need to do is then just divide through by n, with respect to n, and then we get the equation that we're looking for, which is n plus 1, n with respect to n, all divided by n. Just about enough room on my slide, a little bit messy. Okay, so this is actually a fairly straightforward substitution question. Again, the more you do of these kind of questions, the more you get used to it. So make sure that you do. And from this, we need to find 3 approximations for the value of r, which is also reasonably straightforward. So what we're going to do, we're going to write on part C here. And what we're going to do is use this formula. So I'm going to write it again. So r is equal to n plus 1 minus nn over n with respect to n. And we're going to substitute values of t. So we need 3 approximations here. So I'm going to start with t is equal to 1. So when t is equal to 1, okay, we're going to get r is equal to n, well 1 plus 1 is 2, minus m1 over n1. So we're now going to use the data that Jorge has collected to work these different things out. So if we do that, the first one, well, n2 is equal to 52. I'm just reading these values from the table. n1 is equal to this. So you get 52 minus 40 divided by 40. Again, and we're going to work this out. T equals 2 works in the same way. So R will equal to n3. 2 plus 1 is 3 minus n2 divided by n2. And if we use the values given, we've got 70 minus 52. You can probably see the pattern at this point. And so T is 3. I would also show my working, of course. This is why we only get 3 approximations, by the way, because we have no n0. n3 over n3. We'll use the values given, so we have 98. And these are all going to give approximations for R. Okay, so they should all be roughly similar. So let's go over to my GDC and work this out. Okay, so we've got control 52 minus 40 divided by 40 equal to about 0.3. 70 minus 50. Okay, let's just do this as a fraction. Stay consistent. So we go 70, 52 divided by 52, 9 over 26. One decimal for this. 0.346154, and then the last one, so 98. Again, helps with a fraction. 98 minus 70 divided by 70. It's going to give us our approximations. That's 0.4. So I'm going to go back to PowerPoint. I'll just draw it in from here. So we've got, it was 0.3 before. Double check, yep, so 0.3 here. And we've got 0.34154, and then we've got 0.4. So I think it's a 3-mark question. Yeah, 3-mark question, so you've got your data there that we need. All good. Let's carry on. Okay, so we've got the 3 values that we're looking for. Jorge decides to take the mean of these values as the approximation of R for his model, and also decides the model should pass, don't know why, should pass through the point 252. Okay, that's up to Jorge. Find the equation for Jorge's model. So let's just do this in stages. The first thing we're going to do is find the mean. So the mean is going to be equal to those 3 values that we saw. So 0.3 plus 0.346 plus 0.4 divided by 2. So you can do this on your calculator. I'm sure you can do that at home. You should get the value of 0.34871. Now for future reference, because this is going to be our approximate, I'm going to put our A here. This is actually as a fraction 68 over 195. That's going to be easy to use later on. So we've got our mean. So now we need to go back to our very original equation here, which is this one here. So this was our original model. So we've got n is equal to AE. And now we've actually got, oh, wrong page. So we've got n is equal to AE. And now we know R because we've got an approximation for it. So I'm going to write in 68 over 195t. That is a 5. So we'll change that slightly. Better. Okay, and we want to find an equation. We still don't know what A is, but now we can actually use the value that Jorge wants to use. So when t is equal to 2, n is equal to 52. So we're going to substitute it into this model. So this gives us 52 is equal to AE. So the 68 over 195 multiplied by 2, like so. And we can simply work this out using our calculator. So I'm going to try and keep this as straightforward as possible. Remember, this here is just a constant, it's just a number. So we get 52 divided by E. And notice that I'm trying to avoid any rounding errors by keeping it as exact as possible. Okay, so we're going to work this out on our calculator. So let's go back to here, because we're going to need an exact value for A later on. So we go to Control, we have 52 at the top, and we want to use E. E you can access using the pi button here. So we've got E, and we're going to raise this to a power, fraction, 68 over 95 multiplied by 2, and then we get an answer of 25.8887. Now I'm going to store this for later, so I'm going to store this as my A. Okay, so every time I click A, I get 25.8887. That's going to be useful later on. So let's write that in. 25.887 dot dot dot. Okay, so we need to write the model now. So let me go on the next slide. So our final answer, rounded, of course, now to 3 significant figures, is going to be n is equal to, well, our A is 25.9, E, this 68 over 195, 3 significant figures, that's 0.349, T. So that is the approximate model that we've worked out using what we've just done. Good, good. Okay, and at this stage we now need to work out the sum of the square residuals for Jorge's model using the values t equals 1, 2, 3, and 4. This is just a calculator exercise here. So just to remind you what we're actually looking for, so let me do t equals 1 to start with. So when t is equal to 1, we pop this into our formula. So when t is 1, n of 1 essentially is equal to 25.0 e to the power of 0.349 times 1, which makes no difference. So I just want to show you the processes of what we need to do. So we would type this into our calculator. Now this is why I want to use exact values, so we get an exact value for this. Okay, you'll make rounding errors if you do not. So what I'm also going to do is I'm going to store 68 Control 68 over 195, which is our precise answer for R. Okay, and I'm going to press Control Enter, and then I'm going to store this Control and variable. I'm going to store this as R. So every time I click on R, I have that value. So we just want to work out first of all, essentially, so we've got A multiplied by E, so we go to here, and we want the power, and in this case we just want R times 1, yeah? So we get this, and then we get the actually precise value that we're looking for, so 36.6908, like so. Dot, 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 obviously goes on, because it's a float of 6 here. Okay, to work out the sum of square residuals for this particular value, what we do is we take our 36.6908, we minus it from the actual value for this, because remember this is an approximation. We actually know the value at 1, this is 40. So we go to minus 40 and then we square it. Okay, so this is what we're looking for. This is part of the formula used for correlation and regression. So if we work this out on the calculator, okay, we'll get a certain value. Okay, I just want to show you the method here. So what we would do at this point, keep this, is I would take answer and try and keep as easy as possible. answer e minus 40, enter, you get a negative number, we're just going to square it, and then you get your sum of square residual for that particular value. So this one will be 10.9509. Okay, and we're going to do the same for each of these values of t. Now actually for the value of t equals 2 it's going to be 0, but let's show you why that's the case. So we've got n2 is equal to 25.9 e 0.349 times 2. So again we're using those exact values from our calculator. So at this point I will then put in a, I'll use capital A, multiplied by e to the power of r multiplied by 2. We get a value of exactly 52, which is right because this is what Jorge wanted to use as his value for the model. So we actually do get 52 exactly. And so to find out the sum square residual, what we do is we take the 52, we minus it from the initial value of the table, which is 52, it should be, and then we square it, and that will just give us 0 in this case. Okay, so we're going to do the same for t equals 3 and t equals 4. Hopefully that's a clear method at this point. I don't want to take up your time by going through the same thing. If you work these out, okay, you'll get specific values for this, so I'll let you work those out. But then if you add all these together, so what we're going to do right at the end of this process, let me use a highlighter here, we're going to add together this value, what if you work out for t equals 3, and then t equals 4, and then we're going to add all those together. Not with a highlighter, I've done it again. If you're Malaysia Online Tuition, if you're out there, I've done it again. So we add highlighted values together. And if we do that, so you finally get to this stage and add them together, you should get then the answer of 66.1 to 3SF. Okay, so again, I'm happy to go through t equals 3 and t equals 4. It's the same process. You put, for t equals 3 here, you put a 3, you'd work out a value. Whatever that value is, you minus the real value, which is 70, and then square it, and that gives you then this yellow highlighted value here. So we get, oh, and too far, or too far, backwards, there we are. So we get 66.1 as our sum of square residuals, because we've added all those values together for t equals 1, t equals 2, t equals 3, and t equals 4. Good. Right, let me pop up f up here, because this won't take too much room. So we're told actually the sum of the square residuals for these points from the least squares regression model, so a much more accurate model, is approximately 6.555. So comment how well Jorge's model fits the data. Well, our model, our sum of squares, is actually 10 times. So our sum of squares is 10 times the least squares regression model. Therefore, our model doesn't really work very well. Yeah, our model, what does it want to say specifically? Doesn't fit the data well. Okay, and now we need to give 2 reasons for that, so I'll just talk through this part here. So 2 possible sources of error in the construction of this model. By the way, it kind of gives you a hint that the model is not going to be good, just by the second question. The first one, if we go back, are steps. So notice we took a step length of 1 month. I did highlight this at the start. So we took a smaller step, and that would be a more accurate model. And also, by the way Euler's method works, like the trapezium model for integration, that you're essentially going to get an error because of forming those shapes. So what's going to happen here is when you're approximating the gradients, just like you do when you do differentiation from first principles, when you approximate it by a chord, by a line essentially, then you are going to get an error. So those are the two key things to look out for here, as you see on the mark scheme there. So you can see the overall mark scheme, so feel free to have a go through this, but I've explained it, particularly if you're not sure about part E, about where these values come from. This value comes from putting in 25.9 e to the power of 0.349 times 3. Okay, and then you're measuring that against the real value from the table. Okay, and on to question 5. So, a change in grazing habits has resulted in two species of herbivore, X and Y, competing for food on the same grasslands, and at time t equals 0, environments begin to record the sizes of both populations. And they found a model for predicting this change, which is a coupled differential equation. So this is a coupled DE. This is at the harder end of the course. I would really recommend going through this question very carefully. The IB have released a question like this. It uses a lot of the skills that are on the course as well. So make sure you're well prepared for a question like this, more than probably any other question on this paper too. For this system of coupled differential equations, we need to find the eigenvalues and eigenvectors. This is a standard process you simply need to know. It's going to appear on one of the exams, probably a paper 2 or paper 3. So the first thing we need to do is make a matrix of coefficients. So what do I mean by this? Well, I'm going to take the coefficients of the x and y and create a matrix from this. So 0.3 minus 0.1 minus 0.2 and 0.4. Now, everything I'm going to go through here comes from one of the revision guides slides that I'm going to show you now. So let me do this. So essentially everything we're going to do here follows from this slide. So I'm going to make this what's called matrix of coefficients because it's written in the correct form. And we're going to use the information here to actually do some of the later parts of the question. So feel free to pause, take a screenshot, whatever you need to do, so you have these notes ready for you. Okay, so let's now use this matrix and actually find some eigenvalues and eigenvectors. So I'm going to copy this across to here. So you've got 0.3 minus 0.1 and minus 0.2 and plus 0.4. Okay, so the way we work out eigenvalues is we take the determinant of the characteristic polynomial. So what is that? Well, that's lambda I minus a, or the other way around, is equal to 0. So I'm going to break this down. So the I is the identity matrix, so that's 1, 0, 0, 1. So lambda I, and lambda is just a number, we're going to times everything in the matrix by lambda. So 1 times lambda is lambda, 0 times anything is 0, 0, lambda. Hopefully this is familiar to you. And what I'm going to do here is take one of the matrix, this matrix away from this matrix. So I'm going to get the determinant, or lambda minus 0.3 is lambda minus 0.3. And 0 minus minus 0.1 is positive 0.1. The same for this as well, 0.2. You'll notice the mark scheme has this the other way around, but that's fine. And then lambda minus 0.4 is equal to 0. So the determinant of this matrix is equal to 0. Now remember, the determinant of any matrix can be worked out by using the formula AD minus BC for any given matrix A, B, C, D on your formula sheet. So I'm going to do A times D. So I'm going to do lambda minus 0.3 times lambda minus 0.4 minus 0.1 times 0.2 is equal to 0. And so if we expand this out, we get lambda squared minus 0.7 lambda. Now be very careful here. Minus 0.3 times minus 0.4 is plus 0.12. Don't make silly mistakes at this point. It will have a huge effect on the rest of the question. Minus, well, 0.1 times 0.2 is 0.02. Again, being very, very careful with what we have here. We simplify this down, giving us lambda squared minus 0.7 lambda plus 0.1 is equal to 0. Now you can solve this quadratic by any means. You can use your graphical calculator. You can do this by factorizing. There are many different ways. I think a high-level student should be able to factorize this and see, well, we need lambda in both. Two numbers are multiplied to give us 0.1, but minus to give us 0.7. I think we can see that we're going to have these two numbers. Okay, you can check this. So 0.5 times 0.2 is 0.1. And then these two added together gives us 0.7. So we get our eigenvalues of 0.5 and 0.2, like so. Again, feel free to use the quadratic equation solver as well on the GDC. That will also give you these two answers. Right, at this point we need to work out the eigenvectors that are associated. So let's choose one at random. Let's start with 0.2. What I'm going to do now is put 0.2 into my characteristic polynomial. So let me highlight this. This should all be familiar to you from the course. This is a standard procedure you simply need to know. So I'm going to substitute lambda for 0.2 into here. And what you'll notice is we get the matrix of, without the highlight, I think I'd learned this at some point, wouldn't you? Without the highlight, here we are. So 0.2 minus 0.3 is minus 0.1, 0.1. We get 0.2 and then lambda minus 0.4, that's minus 0.2. The two rows should be scalar multiples of each other, or identical sometimes. Good. So we get x and y is equal to 0. So we take any equation, doesn't matter which one. Actually, I should put a and b, sorry. Strictly speaking, but it's the same idea. B equals 0. So we multiply out one of the rows, doesn't matter which one. So we get minus 0.1a. Remember matrix multiplication, we multiplied this by this. Plus 0.1b is equal to 0. We want to get a the subject. This is really important. So we get 0.1a equals 0.1b. And we can essentially see that a equals b, which makes our eigenvector very easy to find, because if we look at our coefficients, both are 1. So our eigenvector with this is 1, 1. And this is associated with the eigenvalue of 0.2. So we've got our eigenvector there. We're going to do the same process with 0.5. I'm going to work it out one way and then use a scalar multiple. I'll show you what I do there. So let's go on to lambda 2 being equal to 0.5. So we put 0.5 into here. So we are going to get 0.2, 0.1, and then we get 0.2, 0.1. Is that correct? Just checking this. Yeah, and in this case, the matrix actually, the rows are the same, which happens. That's good. Okay, just need to be a little bit careful at this point. So what we're going to do then is we're going to write 0.2a plus 0.1b is equal to 0. So this multiplied by this. We're going to get a the subject, so we're going to get 0.2a equal to negative 0.1b. So a is equal to minus a half b. So our eigenvector here, the way we'd write this is we'd write this as minus a half 1. So we're using the coefficients here. Now, to keep this in line with the mark scheme, this is perfectly fine, by the way, having this as your eigenvector. What I'm going to do is make sure I've got a 1 in the top, and you'll see this follows then the mark scheme. If I leave it like this, our constants a and b later will be different, and that might be confusing for you. So all I'm going to do, and you're allowed to do this, because it's an eigenvector, is I'm going to times this whole vector by minus 2. If I do this, I'm going to get my vector here as 1 minus 2. So it's going to be my eigenvector associated with my eigenvalue like so. So if I write the full answers here, lambda 1 was equal to 0.2. This is associated with 1, 1. Lambda 2 is associated with 0.5. And then we have 1 minus 2 as my eigenvectors. All good. Okay, so we've got our eigenvalues and eigenvectors from the first part. So now we need to write down the general solution of the system of equations. This is a case of just using your formula sheet. So if I go to our formula sheet, you'll see here, taking this from Revision Village, the exact solution for coupled linear differential equations is this formula here. Now we know what P1 and P2 are. These are our eigenvectors, and then lambda 1 and lambda 2 are our eigenvalues. So we just need to put everything together at this point in the correct form. So let me go to here. I'll put it in here, part B. So our general solution for any vector xy is equal to A, E. So we're going to take one of our eigenvalues. Let's take the 0.51. The only thing you have to watch out for here is a 0.5t. You need to make sure you've got the right eigenvector with your right eigenvalue, plus B, E, and now we're going to take the 0.2. So you can do it either way around, that's absolutely fine. And then we get our general solution. So for this point, we just actually write this straight away from the formula sheet and put all the right information in the right place. Okay, part C, we're going to do what's called a phase portrait. So we're going to sketch the phase portrait for the system for x, y is greater than 0. And this makes sense because we're looking at real life situation, so no negatives, yeah? We can't have negative 15 herbivores or something. On our sketch, we need to show the equation of the line defined by the eigenvector in the first quadrant, at least two trajectories either side of the line using arrows on those trajectories to represent the change in populations as t increases. So let's just start my sketch first of all. One of the key things to remember, this is always going to be positive. So I'm only looking at the positive axes. And I'm going to go back to those notes that we talked about where this actually determines how our system is going to look. So the first thing I'm going to do is look at eigenvalues. Well, they were 0.2 and 0.5. Okay, so I'm going to write this on my notes here. Lambda 1 was 0.2, lambda 2 was 0.5, or the other way around. So these are both real and they're both positive. Okay, so they're real and positive, so they're going to fit into this kind, an unstable fixed. Okay, so that's what we're going to look at in terms of the equilibrium points. And the trajectories become parallel to V1 as t goes to infinity. Now, if you remember our eigenvectors, we had 1, 1 and 1 minus 2. Now, 1 minus 2 does not exist in the first quadrant. Now you're going 1 along and 2 down. So the only one that is going to appear is 1, 1. Well, how do we do that on a set of normal axes? We're going 1 across and 1 up, 1 across and 1 up. This essentially is going to be the line y equals x, yeah? That 45-degree line that goes upwards. So that's going to give us, first of all, our key line where the actual trajectories are going to go from. So let's write that in. So I'm going to write this in as a dotted line. Let's do this in a different color, magenta. And I was marking that this is the line y equals x. Okay, so this corresponds, I wouldn't write this probably in the exam, but just to show yourself, that it corresponds to 1, 1, which is the one that we care about. And remember, we wanted two lines. So let me do this in, say, blue. So we're going to come out like this and then go this way. Come out like this and then go this way. And we're going to do the same on the x coordinates as well. Like so. If you remember the notes that I did, notice the arrows were pointing outwards. That's important. I've drawn in two lines as well, which is what we needed. Was there anything else that they wanted me to do? That's fine. Two trajectories on either side as t increases. Okay, so you see I've just followed the instructions of the question for the phase portrait. I've used my knowledge of eigenvectors to tell me what kind of equilibrium points exist, and that gives me an idea for how the system operates. Okay, and for part D, so when t is 0, x has a population of 2000. Write down a condition on the size of the initial population of y if it's to avoid its population reducing to 0. So this is just an interpretation of your phase portrait. So notice y needs to be above x. So if it's not above x, as you can see, and it works the other way around as well, then you'll see the population eventually goes to 0. So our condition is essentially that y needs to be more than 2,000. So that's going to be our answer here. Again, they'll get you to do some interpretation of the phase portrait that you draw. They're not just going to get you to draw it and forget about it. And then for part E, it's known that y has the initial population of 2,900, so some more initial conditions. So t is 0, y is equal to 2,900, which we're going to use. Find the value of t at which x is equal to 0. So first thing we need to do is going to write down that solution that we did before. So this is now E part 1. So xy was equal to, just write this down correctly, ae to the power 0.5t, and that was associated with 1 minus 2, plus be 0.2t11, like so. And then we have to essentially treat this as two different equations. So I'm going to basically draw a line right through the middle to see what we're doing. So let me put in Penny's red. So at t is equal to 0. Okay, so we're looking at the initial conditions. So we know that 2,000, because at t is 0, it starts at 2,000. And we're just looking at the top parts. Now notice, when t is equal to 0, e to the power of 0 is 1. So we can kind of ignore that part here. Likewise here as well. And then we're going to do a times 1, which is going to give us a. And then b times 1, which gives us b. So that's our first equation. And then at t is 0, we're now going to look at the bottom. We're going to look at the y part. So here we know the population was 2,900. That's right. And then, again, t is still 0, so this goes to 1. A times minus 2 gives you minus 2a, and then b times 1 is how we're going to use these eigenvectors. At this point, we just have a straightforward simultaneous equation to solve. Notice if I'd written these vectors differently, we'd have different constants, so I'm trying to keep things similar to how the mark scheme does. I think at this point, I would just minus these two equations from each other. So if we do that, we get minus 900 equals 3a, yep, and this cancels, so then we get a is minus 300. And if a is minus 300, we can substitute into anything here, but I think we can see that b needs to equal 2,300. We get that from just substituting in here, so we get 2,000 equals minus 300 plus b, and solving. So that's fairly straightforward. So we then get our values for a and b. So let's pop that into our equation. So xy is equal to minus 300 e to the 0.5t1 minus 2 plus 2,300 e to the 0.2t 1. Okay, and that's our solution to differentials, a couple of differential equations, and we want to find the value of t at which x is equal to 0. Okay, so again, we're just going to look at the top parts of the equation, because we're just looking at when x is 0. Again, if it helps you draw this line, so you know what you're focusing on, by all means please do. So we're only looking at these values. So essentially, we're looking for the solution when 0 is equal to minus 300. This is just 1, so 300 times 1 is minus 300. E to the 0.5t plus 2,300 e to the 0.2t. And you look at this and think, oh, how do I solve something like this? But this is where do not forget your graphical calculator. So essentially, because it's equal to 0, we want to find the roots of this equation. So I've already put this over into my GDC, so let's have a look. So I've already typed this function into my GDC, as you can see, and got myself a graph. And we're looking for the roots, yeah? So we're looking for where it crosses the x-axis. So we go to Menu, Analyze Graph, zeros on a TI Inspire, click before, click after, and then we get our answer of 6.79 years, which is equal to 6.79 years to 3 significant figures. Okay, and make sure you've got the units in there. You don't want to lose a method mark by not having the units. Okay, let's look at part 2. So let me just write in part. No, don't do that. Part 2. Still getting used to my pen. And then find the population of y at this value of t. Give your answer to the nearest 10 herbivores. Okay, so we need to now look at the bottom part of this equation. So we need to be a little bit more careful. So we're working out y is equal to, just looking at the bottom, so minus 300 times minus 2 is 600. Now we know the number of years, because we worked that out in the previous question, at this value of t, so that refers to this here. So we're going to put in that value that we just worked out, which was 6.79. So we've got 0.5 times 6.79, dot, dot, dot. And we just need to be a little bit careful here. So looking at the bottom part, so 2,300 times 1, that's 2,300. E, put 0.2 here. Same value, the number of years, 6.79. And at this point, you just type all this into your GDC. So give you a moment to do that. That should give you the answer of 26,027.9 dot, 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 dot. Remember, the question wanted us into the nearest 10 herbivores, so we are going to round here. So 7 is going to round the 2 upwards, so we get 26,830 herbivores to nearest 10. Right, just want to quickly show you the mark scheme. So here's the mark scheme here. Notice I did my characteristic polynomial the other way around. That's perfectly fine. You'll still get to the 2 answers here. Working through, just to keep your life easier, I would normally write this as this, so minus a half 1. It'll give you different constants, so I've tried to keep it similar to the mark scheme. But notice equivalent forms are perfectly fine, so they would accept this as an answer. We get our general solution, like so. Phase portrait, you can see needle line y equals x marked clearly, arrows going this way and then landing onto the y and x axes respectively. Y is greater than 2000, and then working through the algebra here to get these marks. Okay, so I'm going to stop here for this particular video. Again, if you like the content you are seeing, please like and subscribe. It helps me know that IB high-level applications is what's wanted on my channel, so that's really, really good to know. So I'll go through question 6 a bit later on. Bye-bye for now.